I'm Andy Fabian. I'm the Acting Director of the Institute of Astronomy here at the University of Cambridge.
So tonight's voyage, we turn from the oceans to astronomy. Now, in his essay on the Areopagus, the Hill of Mars, John Milton, the poet, tells us that he had found and visited the famous Galileo, grown old, a prisoner to the Inquisition for thinking in astronomy. He'd participated in the Italian academies. These were the ones who went to the extreme, who, by finding new worlds, changed our world and thinking. Milton, though, defines what we hope to be here in Cambridge, not slow and dull, but of a quick, ingenious, and piercing spirit, acute to invent, subtle and sinewy to discourse, not beneath the reach of any point, the highest that human capacity can soar to. The highest point. That's the extreme where astronomy pulls us. That's what we hope this university is doing. Now, but Mars, I expect, that most people may think of a couple of things if I say Mars. One, of course, Mars rover, the planet, the red planet. The other, of course, though, is the chocolate bar, made in Slough. Slough was where William and Caroline Herschel lived. Keenly supported by their neighbour across the Thames in Windsor Castle, William was George III's astronomer. Caroline put together the new general catalogue of thousands of nebulae and star clusters, including many of her own discoveries. And our modern study of the universe comes from that catalogue, for which the Royal Astronomical Society awarded her their gold medal. She was the first woman to be awarded that. Astronomy fascinates us, unimaginable worlds beyond our own, and tonight, to explore those extremes, we have one of the world's eminent astronomers, astrophysicists, Professor Andy Fabian, Director of the Institute of Astronomy here in Cambridge. Like Caroline Herschel, he's a gold medalist of the Royal Astronomical Society. He's also a fellow of the Royal Society and a foreign affiliate of the US National Academy. These are the descendants of Galileo's academy, the Lince or link side, the far-sighted ones. And he's a fellow of Darwin College and the central guiding individual behind this annual Darwin College lecture series from the very first series in 1986. So please welcome Andy Fabian to speak on extremes of the universe.
Thank you. Well, thank you very much. Talking about the extremes of the universe, I'm spoilt for choice. One of the extremes, of course, is the Big Bang, which is the origin of space and time that started it all, but I'm not going to go and talk about cosmology. I'm going to talk about the extremes of power in the universe, the most powerful things. I'm looking at our nearby powerhouse, the sun, in this little movie, and you can see all these eruptions of material above it. These are solar prominences, which are visible in the light of hydrogen alpha, and we're going to go on and look a bit at those things. But in a sense, what the theme is, it's going to be about power in the universe. What are the most powerful objects in the universe that we can see? And often it's involving magnetism. Sometimes it's gravity, most often gravity and magnetism, that is driving what I'm going to talk about. So I'll move ahead, looking at these eruptions from the sun connected with solar flares. The sun is actually a very inactive star compared to many stars out there. It's a dwarf star, and things about our solar system are not very eruptive like this, thankfully for us, I think. But what we've got on the sun, the sun, as you know, has not got a solid surface, but it's a gas ball. and it's rotating, not this fast, in this little X-ray image up here. It rotates at 26 days at the equator and at 30 days at the poles. This means it's differentially rotating. And if you differentially rotate a magnetized plasma, it's like winding up a basket full of rubber bands. Eventually they start springing out. And here are the rubber bands, the magnetic field lines, springing out from the surface of the sun in this picture down here, taken in the ultraviolet. But sometimes there are really enormous eruptions on the sun, so-called solar flares, and perhaps the brightest solar flare seen in historical times was recorded by R.C. Richard Carrington, Esquire, while engaged in the forenoon. How many of us talk about the forenoon of Thursday, September the 1st, taking my customary observation of the forms and positions of the solar spots? An appearance was witnessed which I believe to be exceedingly rare. And that is in this drawing here, it's these white bits just here, and what we refer to as a white light flare. Now, white light flares on the sun are very rare. He's the only one to have seen one, and it was verified by somebody else, so it's a genuine observation. But it coincided with the observation of the aurora. This is a painting of observation of the aurora as far south as the Caribbean. Also, back in those days, they had telegraphs connecting cities, ran along railway lines and things. They were long wires, and people were getting sparks off them, and things were being set on fire by them. This is because there was an enormous eruption from the sun at the same time of plasma coming out directly towards the Earth, and that plasma striking the Earth a few days later, giving rise to all these phenomena. Essentially what you've got is the Earth's magnetic field is encased in this solar wind all the time, but there's a big eruption passing through it. It squeezes the Earth's magnetic field, and everybody knows from Faraday's law that if you move a magnetic field, you generate an electric field, and those electric fields lead to all of this phenomena and also the sparks. And were one to happen today, it could easily wipe out many of our transmission systems and wipe out our satellites, particularly the GPS satellites. The next time one happens, they're not predictive, we can't predict when they occur. The next time one happens, I don't want to be landing in an aeroplane. Now, it was thought that these were extremely rare and haven't happened recently, but actually we have got two satellites monitoring the sun, one ahead of us in our orbit, one behind us in our orbit by about 60 degrees, and they're called Stereo A and Stereo B. And you're now seeing the whole of the July the 23rd, 2012. That's the sun in the center. It's not an image, it's just an image pasted on. This is a disk blotting out the image of the sun, and you can see in this speeded up movie, you can see that something is erupted from the sun. Here it goes, this vast coronal mass ejection it's called. But notice how this image suddenly gets terrible. It's full of spots. That's because there's a vast cloud of very energetic particles coming out as well, and those energetic particles, which come out only slightly slower than the speed of light, are then bombarding that satellite with this intense, it's very intensely irradiated. That's what causes a lot of damage to satellites. It's what we don't want. So this was 23rd of July, 2012. Had it happened just a week earlier, it would have happened directly at us. So 2012 would be known to all of you. This date would have been known to all of you had it happened, or let's say it would be 16th of July 2012 would be known to all of you if the alignment had been different. So are solar flares the biggest things that happen on the sun? Well, this is just a technical plot, but this is the frequency at which flares occur versus their energy. And don't worry about the units, but what we've got, each of these ticks is a factor of 10. So, this is 10 to the 24, 10 to the 26, that's a factor of 100, that's a factor of 100, that's a factor of 100. In order to plot anything, and I'm going to show you only a few plots, but I'm going to talk about big numbers. And the only way I can talk about big numbers in astronomy, because they are astronomically huge, is to talk about them in powers of 10. So when I say 10 to the 20, that means a 1 followed by 20 noughts. 10 to the 40 is a 1 followed by 40 noughts. 10 to the 52 watts, we're going to get there. 10 to the 52 watts is a 1 followed by 52 zeros watts. Well, here we're talking about 10 to the 32 ergs. This is the total energy in a flare. And you see people have looked at the rate at which flares occur there. Do they also occur up here? Well, you can, if you work it out, these flares up here, were they to occur, would occur once every 1,000 years or so. So we have to look at the sun for 1,000 years to see one of these super flares. But another way to do it is to actually look at 1,000 stars, like the sun, for a year. And that's what's been done with the Kepler satellite, just staring at 1,000 solar-type stars, and they do see these flares, and it continues up there. So we don't quite know where this ends, and there's probably some physical limitation, but they can be extremely energetic. And this is just a dwarf star. Unlike the sun, it's smaller than the sun. A small red dwarf star actually had a flare that big in 2014. Now I'm going to go on now I'm doing the preliminaries before we get into all the exciting details of all the powerful events in the universe. I want to talk you through a little bit about how big power can be. How large can you think about the maximum power? And I'm going to send you all out of the room because I'm going to give you an equation, which everybody says one shouldn't do. But this is a very simple equation. It's just what is the maximum power that you can get from an object of mass m. And so it's very simple, but if you've not seen it, it's very cute, at least in terms, I think it's cute. But this is the power or luminosity. It's defined as energy divided by time. You all know about light bulbs, 100-watt light bulbs or 15-watt light bulbs that you use. So that's a unit of power. So it's energy divided by time. What's the maximum energy you can get from mass m? Einstein gave us the answer. It's mc squared. And I'm sure everybody in this room knows E equals mc squared. So there's energy equals mc squared. What's the shortest time that you can get it out on? It's what we call the light crossing time. It's how long light takes to cross the object, because the fastest you can remove the energy is at the speed of light. And of course, if you want to get a pulse from it, you've got to have the light from the back side, and you've got to see the light from the front side, and there's a time difference between the two. So that's r over c. Rearrange that, we get mc cubed over r. And then what's the smallest radius it can be? What's the smallest radius a mass can be? It's a black hole. What's the side of a black hole? It's gm over c squared, if it's spinning. Okay? So I now rearrange it, and the m cancels, and I get c to the fifth over g. And that's the maximum power that you can generate from an object. C to the fifth. C is the speed of light, which is a very large number. G is the gravitational constant. Gravity is not a very strong force. It's a small number. A very large number divided by a small number. It turns out to be 3.6 times 10 to the 52 watts. Okay? That sounds utterly ridiculous, utterly ridiculous, but it's not completely ridiculous. It turns out to be the maximum power is 10 to the 26 times the luminosity of the sun. Okay? Now it turns out that in our galaxy there's 100 billion stars, and there's about 100 billion galaxies in the universe. So if I take the power of all the stars in the universe and then add them all together, that's going to be 100 billion times 100 billion, that's 10 to the 22. So this maximum power is 10,000 times bigger than all the luminosity of all the stars and all the galaxies in the universe. But this is my maximum. Another limitation on power in the universe comes from what we call the Eddington limit. 100 years ago, one of the most prominent astronomers in the last century was Sir Arthur Eddington, a Plumian professor here in the University of Cambridge. This is named after Eddington, pointed out there's a limitation to how powerful something can be, because power, because radiation, and if you've got something radiating, radiation exerts a pressure. We have all seen pictures of this. This is Comet Hale-Bopp that the older members of the audience will remember from about 20 years ago. And this is its tail, or tails. This is the so-called iron tail, which I'm not interested in. This is the dust tail. And basically, the sun is way over on the left here, and the radiation from the sun is blowing the tail away from the comet. And this is very visibly demonstrating that radiation pressure can push things. And what you can get, there's a limit to how powerful something can be in terms of radiation when the radiation is so powerful it blows the thing to pieces. So that if radiation outwards is equal to the gravitational pull inwards, greater than the gravitational pull inwards, then obviously the object will blow itself to pieces. And that's called the Eddington limit when you're there. And this is a plot showing power up there versus mass of objects in the universe. And I'm again using this logarithmic unit. So 0 means 1, it's 10 to the 0. That's 10 billion, and so on. The sun's down this bottom part. This is the Eddington limit. There's the ultimate or maximum power. And it turns out stars are down here, galaxies up here, and all stars in the universe up there. Now we're going to start thinking about exploding stars. So in order to talk about exploding stars, I want you to think about what stars are and what's going on in stars. And I'm going to do this in terms of this mass-radius plot. Don't get too worried about it, but this is mass and radius, and astronomers like plotting everything in the universe all on one plot. And so we've got logarithmic units again, okay? And stars are over here, with the sun there on one of these units. And these are black holes. These are planets. And when you get up here, this sort of turns round and goes down to these objects called white dwarfs. Incidentally, white dwarfs were first understood by the master's grandfather, Ray Fowler. This turning point here is known as the Chandrasekhar mass. There's a maximum mass to a white dwarf, and it's up here. Down here, there's another point at which you can have stable objects. This defines where stable objects occur. White dwarfs, planets, that's Jupiter, that's the Earth, and neutron stars are over here, just before you get to black holes. There's nothing that is made that what we would see as a solid object above, in this part of the diagram, above the white dwarfs and neutron stars. You then have the black holes, which are objects which I'll get to later, where they've collapsed in on themselves. Stars are over here, and they're held out over there because they have nuclear reactions in their cores, which generate a pressure in them, which balances gravity. And so in the sun, we've got the outward pressure, thermal pressure, due to the creation of all the helium in the core of the sun from the hydrogen there, nuclear fusion. That's actually inflating the sun, keeping it in balance. And the sun's been like that for the last 5 billion years. But eventually, you end up using up all the hydrogen in the core of the star, and it then collapses, the core collapses, and starts burning helium to carbon, and eventually the sun will die as a carbon-oxygen white dwarf. So there I've represented this by an arrow. The sun will end its life as a white dwarf. It will throw some of its outer envelope away, but it goes like that, and it will get stuck on that bit there. But if you're a more massive star somewhere up here, then what happens is the only thing the core of a star can do is collapse all the way down and form a black hole. There's nothing else for it to do, and in doing so, because the material of the star, the core of the star, collapses inwards, there's nothing to stop it collapsing down, and there's an enormous amount of energy being released. And it does it very quickly. It collapses down in a matter of minutes and seconds, enormous amount of energy, vast explosion. That's what we call a supernova explosion. There is just one other one of these, and that is if you're a medium-sized star, then you can actually go across here, throwing off some of the mass on the way, and you can end up as a neutron star. So I'm now going to introduce you to supernovae and neutron stars, starting off with the only supernova. That's the supernova explosion. That star exploded. That's what it looked like beforehand. It's this thing in the middle. This star exploded in 1987 in February in the nearby galaxy called the Large Magellanic Cloud. It's a satellite galaxy of our own. This nebula is a nebula of gas. You can see it in the light of hydrogen there. It's called the Tarantula Nebula because it looks a bit like a squash spider. Anyway, this thing was extremely bright and visible to the naked eye. It's the last one that's been visible to the naked eye. And this is just a plot of its brightness versus time. That's a year. And you can see the thing actually was not observed down there. And then suddenly, very quickly, it brightened up and made this brightness and dropped down like that. And when it's below this level, it's too faint for the human eye. I actually was observing at the Anglo-Australian telescope in late '87 and saw this supernova through binoculars. I didn't come early enough to see it with the naked eye. So I've never seen a naked eye supernova. This part of the curve in this plot, which is straight like this, is due to radioactive decay. When you get a supernova explosion, the temperature is extremely high, and they go and in the ejector, as it's all thrown out, there are lots of neutrons, and that leads to many of the heavy elements, the elements greater than hydrogen and helium that we have around us. Most of us I don't know if you know this, but the dominant element in your body by mass, if I was to go around and ask you, most people would say carbon. Actually, you're wrong, it's oxygen, okay? Now, if I was to get a stone and do the same, what's the dominant element in a stone? It's mostly oxygen. The geologist in the front there is nodding in approval, so I think I've got that right. Anyway, so oxygen, but in our bodies, okay, most of the oxygen in our bodies was formed in one of these supernova explosions. So, you know, all of this, we are stardust, etc., but that's where most of the oxygen comes from. And about half of the iron in your blood comes from what's called a core collapse supernova. These are the supernovae where the core of the star has collapsed, as I've shown you. And this, I think, is a wonderful image. Is made by the EROS-2 collaboration. And this is speeded up images of the region. The supernova occurred here. And this is speeded up images over the 7 years from 1996 to 2002. Can you see these ripples going outwards? These are just where the light from the supernova is now reflecting off the nebulae here. Okay? These nebulae have got dust in, and if you shine a bright light on dust, it shows up and it can reflect, and so you're seeing the reflections, and you can see them going across here, so they circle around there. So in a way, this means you can look back in time, if you see that, and you can actually go and measure its color and so forth, you're actually looking at a reflection of the original supernova. So when you're out there in a clear night and you shine a torch around, that torchlight goes out into space and may reflect off dust grains. And if your torch was really powerful, you could see it back again. But these you can see. This is another core collapse supernova in our own galaxy in the constellation of Cassiopeia. And this occurred in the 17th century, and it's not clear that anybody saw it. There's still a squabble about whether anybody saw the flash from it. But you can see the outer shock wave as it's propagating out into the gas between the stars, and you can see the inside of it there. Now, there's another class of supernovae I just wanted to mention. because I'll be talking about mergers of binaries again later in the talk. And these are white dwarfs. I said how the sun is going to end its life as a white dwarf. Now, our sun is unusual in a way because it's a single lone star. Most stars in the galaxy, more than half of stars in the galaxy, are multiple stars, meaning there's not just one star, there's several stars. And sometimes there are two stars which are close together, and both of them can evolve and become white dwarfs. And they can be driven together by the radiation by gravitational radiation, which is something I'll get to near the end of the lecture. And they can spiral together like this. And when they do that, it leads to a giant thermonuclear explosion where the brightness when it goes bang is about 1 billion times as bright as the sun. That's its power, not how bright it appears to us, but is 1 billion times the power from the sun. And there is a nearby galaxy, M82, with before and after when a supernova occurred back in 2012 in that galaxy. And that was this kind of merger of white dwarf supernova. And those supernovae mostly leave iron behind. And the other half of the iron in your blood comes from that kind of supernova. Now, the brightest flash that's been recorded by anybody, flash to the eye, occurred at the generation of this supernova remnant. This is the remnant of a supernova that occurred in 1006. And it was seen, the supernova explosion was actually seen by Korean, Chinese, and other astronomers and recorded. And that's where it is now. This is the remnant of a core collapse supernova, and it's called the Crab Nebula because Herschel thought it looked a bit like a crab, but I can't see that myself. But it's a very strange object, and this is the remnant of the supernova that occurred in 1054 AD. This is in the constellation of Taurus, and when it was going off, it would have been easily visible in the daytime. There are absolutely no records from England. Maybe everybody was going around looking at the ground all the time, or maybe it was cloudy all the time. But anyway, it was not seen, but it was again recorded by Asian astronomers. And I think it was also recorded by some monks in Switzerland. Now, this supernova of AD 1054, which is only 48 years after the 1006 one, so it was possible for somebody to have seen two supernovae in their lifetime. This one has left behind a neutron star. And it was long thought that there's something funny about one of the stars in the center of it, and it wasn't until 1968 it was realized it was a pulsar. A pulsar is essentially this collapsed object at the center, only it's highly magnetized, and as it spins round, it flashes at us. And it flashes in all wave bands from the radio through to the gamma ray bands. And this is the pulsar, that thing there, and you can see that it's done something to the nebula around it. And that's because it's a highly magnetized neutron star. The neutron star has got a size of a radius of only 10 kilometers, so it's about as big as London. It's rotating at 30 times a second, so it's spinning pretty fast, and it's got a magnetic field of 1 million Gauss, or million times the magnetic field in this room. I'm now going to just play you what it sounds like. That's 30 times a second. There are pulsars out there that are much faster. And I'm now going to remind you of your last visit to the dentist, because this one is 600 times a second. You ready? I thought you'd like it. So these are pulsars. Pulsars are the dead remnants of explosions, exploded massive or medium mass stars, and they're quite common in our galaxy. There are also kinds of neutron stars which have got extremely high magnetic fields that are 1,000 times higher than the one I just talked about. So there are 1,000 million times the magnetic field in this room. These extremely high magnetic fields mean that the crust of the star is incredibly stressed by the magnetic field, and sometimes it cracks and breaks. And that leads to an intense flash of radiation, most of it in the gamma ray and hard X-ray bands. And these objects are known as magnetars. And this is the most intense flash that's ever been recorded, most powerful flash, it's the brightest flash, this one, and it occurred in 2004 in December. And this is just a time running along there where that is a minute, another minute, and so forth. And there's this incredibly intense flash. And indeed, in this instrument, it's totally saturated. And the only way they got good measurements of the brightness of this flash is by looking at gamma rays reflected off the moon. And the moon is not very shiny at all in gamma rays. In fact, it mainly absorbs them. So this is a really intense flash. And as I say, it's the brightest flash that's been seen. And it comes from the other side of the galaxy. And as it decayed, it showed a pulsation. Okay, can you see the pulsations there? Every 5 seconds, that's due to its spinning. These flashes of gamma rays hitting the Earth's atmosphere ionize the atmosphere, and indeed the oscillations could be picked up by radio measurements of the outer atmosphere, outer ionosphere of the Earth. So it set the Earth's outer atmosphere ringing like a bell. So something the size of London, the other side of the galaxy, goes bang and causes our atmosphere to ring like a bell. Okay? If you wanted to do real astrology, we should all do gamma ray astrology, because these are the things that really do affect you. I'm absolutely 100% convinced that the position of Saturn in the solar system on the day you were born has got no influence whatsoever, any influence whatsoever on you personally. I'm now going to turn to black holes, and just to show you the evidence for the one in the center of our galaxy. These are all stars in our galaxy. This is the Milky Way. The dark bands are due to dust, and the center of our galaxy is there. Everything in our galaxy rotates around the center at about 230 kilometers per second. If you go in and look at the cluster of stars at the center of our galaxy, particularly in the infrared band, this is where the center is, just there. You need to remove the flickering, the deviations caused by the Earth's atmosphere in order to do this, and this is called adaptive optics, where basically you create a star in the outer atmosphere of the Earth, and you sharpen your images up on that, and as they switch it on, you can see the image gets very sharp here, so that you can actually see the motion of the stars. You make the artificial star using these laser beams. These are the Keck telescopes on Hawaii, shining laser beams at the galactic center. The galactic center is 25,000 light years away, so if they were to send a signal, it would take 25,000 years to get there. So I don't think if there's anybody at the galactic center, they're going to take much notice of that. But anyway, here is what they can see in terms of the motion of the stars, and you see the stars are doing something moving around the center here. If we now look at that, these are a plot of all the motion of those stars, and there's one of the stars, I'll go back, it's this one, is orbiting the center about once every 15 years. And that's this star. And when it was going close to this point, it's orbiting around this point in an elliptical orbit. When it's close to this point, it's traveling at 4,000 kilometers per second. This is the radial velocity of it, and these are the positions of it. Using Newton's equations of gravity, you can work out the mass of the object there. That mass turns out to be 4 million times the mass of the Sun. 4 million times the mass of the Sun. And yet, it has to be a very compact region because it follows an orbit very precisely. How compact does it have to be? It has to have a density which is more than 10 to the 19.5 times the mass of the Sun per cubic parsec. You probably don't know what a cubic parsec is. It's a distance measurement in astronomy, but essentially it's the distance, a parsec is the distance between us and the next star, approximately. So our local density of stars is 1 in these units. This is 100 million times higher than the density locally to us. It can't possibly be made of stars because it will be incredibly bright. You can't even make it out of neutron stars without the neutron stars colliding with each other. There's nothing known to physics that can be there other than a black hole. Now, black holes also are powering quasars, but let me go on to the concept of the black hole. This is from Einstein, the idea that mass warps space-time, and here it's shown warping the space just in a two-dimensional representation, and it's something where the center has collapsed, warping the space around it, and there is an event horizon around it, a little bit like a waterfall. This is Niagara Falls, of course, but you've got to think about this edge round here as being a point beyond which you can't come back, and we call that the event horizon. As you approach the event horizon and are observed by an outside observer, you go from looking yellow to red, you appear red-shifted, and eventually time appears to stop. If you had a clock, your clock would appear to stop by the time it gets here. You never actually appear to the outside observer to fall into the black hole. So black holes were originally a theoretical concept and originated in the 1780s by John Mitchell, who was a fellow of Queen's College but spent most of his time looking after a parish in Yorkshire. But he theorized that if he was to pack lots of suns together, lots of stars together, eventually they would have an escape velocity from the surface bigger than the speed of light, and therefore you couldn't see them. That's a Newtonian argument which isn't right nowadays, but he essentially got the right answer. But then Einstein came up with his general theory of relativity, and that gave rise to the concept of black holes. The equations were solved the following year, just 101 years ago, by Carl Schwarzschild for a stationary point mass, and then for a spinning object back in 1963 by Roy Kerr. I now want to show you about black holes by just showing you a picture of the sky. This is the visible sky, and if there are any amateur astronomers amongst you, you'll recognize this pattern. This is the constellation of Orion with Betelgeuse there and Rigel there, and that's the brightest star in the sky, Sirius. This is the moon, and that's the constellation of Taurus the Bull. I'm going to switch now to what the sky, the same patch of sky, looks like in the X-ray band. There it is. And then you can see the stars in Orion's belt. I'll flip back. You can see Orion's belt. And they're showing up because of magnetic activity, like we can see on the sun. You cannot find Betelgeuse in this picture. The moon is that thing. This bright thing here is the Crab Nebula, which I've already shown you, which has got the pulsar in. So it's a dead star. And this is Sirius, but not Sirius A. This is its white dwarf companion, Sirius B. So in X-rays, you see Sirius B, not this bright star, which is Sirius A. They orbit each other every 50 years. So in this picture in X-rays, you see dead objects, white dwarfs, neutron stars, some active stars, magnetically active stars, and many, many black holes. Most of the objects you can see are black holes. And here we can see black holes. Now, I've just said things can fall into a black hole and you can't see them. They can't go out. How can you see black holes? You see black holes because material falls into them. They are the ultimate thing to drop material into, and you can release the greatest amount of energy by dropping material into a black hole. And this is just an X-ray image of a patch of sky, and 95% of the dots there are black holes accreting material from their host galaxy. Some of these things are clusters of galaxies, the big fluffy ones. There is an artist image of one of these black holes accreting material in the form of an accretion disk. We expect the matter to swirl around, and sometimes the magnetic fields generate powerful jets that come out of them. So accretion, dropping matter into black holes, generates enormous amounts of power. And just to go through some numbers with you, this is E equals mc squared, but with an efficiency factor, for chemical reactions, that is 5 times 10 to the minus 11. It's a very small number. Chemical reactions are very inefficient in E equals mc squared. Nuclear fusion is 100 million times better, and that's what powers the sun. So clearly, you're getting a lot of energy out for your mass. And indeed, if you were to take your petrol from your car and enable it to undergo nuclear fusion rather than chemical reactions, you'd go 100 million miles per gallon, or should we say 1 billion miles per gallon. You can go even 20 times better than that if you can go to black hole accretion. If you drop matter into a black hole, you can release more than 10% of its rest mass. So small amounts of matter in galaxies falling into black holes at the centers produces an enormous amount of power. I've shown you pictures of the black hole at the center of our galaxy. It is not very bright. Somehow it's not got much material falling into it. In many other galaxies, they are very bright. And what they do in this brightness is essentially blast all the gas out of the galaxy. And we think that this is the reason why many of the elliptical galaxies, the most massive galaxies in the universe, are mainly these big balls of stars. They all look now red and dead, unlike spiral galaxies, which have got lots of star formation. We think that's because the black hole at the centers of these galaxies has blown all the gas out of the galaxy. In blowing all the gas out of the galaxy, they stop any new stars forming. There's no gas to form new stars. This is amazing. This has been a realization in the last 20 years. It's the black hole at the center of the galaxy that controls the mass of the whole galaxy. When a galaxy ends its life, it's due to this tiny little thing, spatially tiny. It's actually got 1,000th of the mass of the galaxy, but it's physically very tiny. It's got a size, the black hole at the center has a size compared to the size of the galaxy, a bit like the size of an orange compared to the size of the Earth. Okay? That's an extreme for you. Okay, imagine something that small controlling something that big. It's got 1,000th of the mass, but small amounts of matter falling into it blast all gas out of the galaxy. That's what we think is happening in quasars. Moving on, there are these jets that come out of them, often powered by the magnetic fields. And if we happen to look down the jet, those objects can look even brighter. So this is very bright, but if you look down it, it's going to look very, very bright. And actually, one of these objects at quite a high distance, and for anybody who's an amateur astronomer, they might know about redshifts. And redshift 1, there was a quasar at redshift 1 visible in binoculars just over Christmas because its jet pointing at us underwent an enormous flare. These jets can go out beyond the galaxies. This is a large galaxy, and it's squirting these jets out either side, making these enormous lobes. This is actually emissions seen in radio wavelengths overlain on an optical picture of that region. And these jets can lead to interesting phenomena. This is the nearest jet that has been seen. It's in the constellation of Virgo in a galaxy called M87, and here's this jet sticking out that side. You cannot see a jet the other side. This was found 100 years ago by Heber Curtis, who wrote that there is a thin white ray emerging from the nucleus of M87. He didn't know what it was. And do you know, we don't actually know exactly what it is even now, 100 years later. We know it's squirting electrons out. We know that because of all sorts of things, including the fact that light is polarized. I'm not going to define what that is if you don't know. But basically, that means it's got negative particles coming out. We don't know what the positive particles are coming out, whether they're protons or positrons. Maybe it's squirting antimatter out. I think it's squirting antimatter out, which is rather interesting. We cannot see the other side. We think they're jets going out equally either side. We can see that one. Why can't we see the other one? Well, we can perhaps start to understand it if we look at this Hubble image of it. It's been tipped round to make it level here. There's the jet I've just shown you there. We're going to look at this bit of it here. And can you see in the 90s, Hubble saw there's clearly something emitted and is moved across like that. If you work out the distance it's moved, it's gone 24 light years. It's gone 24 light years in 4 years. So it's traveling at 6 times the speed of light. Okay? Is that all right? I'll have one of those, please, because that's how I can travel around in space. It's superluminal. It's actually an optical illusion. Even those ripples from the supernova were traveling faster than the speed of light. Okay? It's due to the fact, in this case, that this jet is pointing towards us, and the matter in the jets is traveling very, very fast. It's going very close to the speed of light. It's chasing the light beams, and you can do a very simple geometrical calculation, which I am not going to do here, show that you can end up with this apparent superluminal motion. Now, the most amazing jets that we see are these ones, and they're associated with gamma ray bursts. These are intense flashes which were first found in the 1960s by the military. Both the Soviet and the US military were monitoring outer space, hoping to check that each other were not letting off nuclear bombs in space. These are monitoring satellites. They did find flashes of gamma rays that you would expect to see from a nuclear bomb, excepting these flashes of gamma rays clearly came from beyond the solar system. They did not come from nuclear weapons. I mean, people did at one point say, well, maybe there are other intelligent life as letting off nuclear bombs, but no, that's not the answer. These flashes like this are associated with the birth of black holes in stars. And basically what happens is during the supernova collapse, forming a black hole, if the material is spinning very fast, it's able to make jets which squirt through the whole star and out through the star. And if it's shining at us, and I'm not going to point this laser beam at you, but you know a laser beam pointed is very bright along the laser beam. It's like having a laser beam shone at you. That's what we're seeing here. These things are very bright in gamma rays. They're gamma ray bursts. And for anybody who knows about relativity, these jets have got a Lorentz factor of 100, and this thing has got a Lorentz factor of 10. But I'm not going to go any further in defining it. These are extreme objects in the sense they've got extreme powers. Now I'm on my last 10 minutes, I'm going to go through 2 final classes of objects. These are fast radio bursts. They're the mystery of 2017. They made the cover of Nature in January, the first issue of Nature this year. These fast radio bursts were first discovered in 2007. These slides were given to me by Jason Hessels, of a Dutch astronomer. Now, that's the Parkes Radio Telescope here in Australia. And it picked up one intense flash in 2007. That's when it was published by Duncan Lorimer, so known as the Lorimer burst. It's an intense, very bright flash. These are that's 100 milliseconds, 200 milliseconds, so that is half a second. So it's a very sharp flash. It also changed, this is now frequency, and it changed in frequency. So essentially in radio frequency, it was first detected at high frequencies, and then it decayed and was seen in the lower frequencies. This is called dispersion of the radiation, is characteristic of radio signals going through ionized gas. And this looks like it could be the gas between the galaxies, or it could be gas associated with the thing itself. Apart from the fact that the radio telescope was pointed at a particular region, Duncan Lorimer had no idea what this is due to. It was clearly very sharp and very bright. People then began to wonder whether there were any other ones. Time passes, people are getting frustrated, they can't find any more bursts. Nobody found any more bursts. And then there were some bursts seen, also from the Parkes radio telescope. They looked a bit like the original one, excepting they were a bit sort of spotty. There's something funny about them. They don't quite look right. And what they were due to was somebody opening a microwave door nearby. It took a while to work this out. But they're pretty certain that this one is not due to somebody opening a microwave door, okay? And so it remained as a big puzzle, what's going on here, until in 2013 another burst was seen, and a few other. This meant there's a population of fast radio bursts. People didn't know what they were. Because these radio telescopes are only looking at a tiny patch of sky, there must be thousands of these over the whole sky per day. But what are they? And these are all the ideas. Are they pernicious radio frequency interference or atmospheric effects? Flare stars, we've already heard about flares. Are they microquasars, pulsars, magnetars? Or are they SETI? Are they little green people? Okay. Can they be something new? Gamma ray bursts? Supergiant pulsars from pulsars? Evaporating black holes? Stephen Hawking? Supernovae? Merging black holes? I'm going to talk about that in a minute. We don't know. And then another one was found from the Arecibo telescope. You can see it's not a great one, but there it is. And this is the start of working out more what they are. This came from this Arecibo telescope, which many of you remember if you like watching Bond films. They fought on here during the film. And which film was it? GoldenEye. Well done, thank you. Yeah, I always remember the eye bit because this is an eye on the sky. Okay, so there we are. Anyway, it came from there. Okay, this is a globular cluster. This is the plane of our galaxy, the Milky Way. So it came along the plane of our galaxy, but it's not obvious it's galactic. And then they found more from the same position. So it's not due to a cataclysmic explosion, something blowing itself to pieces. It's repeating. And you can see there are many more of them. You may wonder why they're not all shaped like that. That's because somebody straightened them all up just to pack them all onto a simple plot. So really important, it rules out a cataclysmic source. It's not a single explosion. It's due to a pulsar on steroids, perhaps. And they even worked out where it came from. Because it repeats, they even found there was a constant source at the same position. They were able to combine a whole load of radio telescopes, Arecibo and the European VLBI network, and there's a map of it, and you probably can't read this, but this one here is, this one is Cambridg. So anybody who drove up the Barton Road will have driven past the telescope. The big dish there is part of this, this European very long baseline interferometry network. By using all these telescopes at the same time, looking at the same patch of sky, they can get a very accurate position. And the net result is it came from this object. Okay? It came from that object. And you can see it doesn't look very exciting, does it? So this burst came from there. This is the cover of the first Nature of the year. So this is where it comes from. It's a very faint object. It's 100 million times fainter than the naked eye limit. The galaxy it comes from is 1,000 times less massive than the Milky Way, I showed you that supernova 87A came from the Large Magellanic Cloud. The Small Magellanic Cloud has about this mass. So it came from a little tiny galaxy. And each burst, when it goes, briefly outshines all the other stars in the galaxy. And it looks like this object is the Small Magellanic Cloud, only at 3 billion light years. So these bursts we're looking at happened 3 billion years ago. What are they? We don't know. I think, and many people think, they are actually due to a very young magnetar. Okay? If a magnetar were formed, maybe 20 years ago, we never saw a supernova from there, but then maybe we wouldn't have done, and maybe it's left behind one of these magnetars. It remains a puzzle. Now into the last part. One other class of flare that you can get is when a star strays close to a black hole and is ripped apart by the tides. I don't have time to talk about those, but I'm going to talk now briefly about gravitational waves. When you get binary stars spiraling together, when they orbit each other, they cause warping of space-time and they cause gravitational radiation. And this is meant to represent ripples of space-time flowing away from this binary system. You can get binary stars of different types. White dwarfs we've already spoken about, but you can also get neutron star binaries. Here they are. And these are the temperatures, so going up to 100,000 million degrees. When you merge two neutron stars together like this, you probably get a gamma ray burst, and you also generate a lot of heavy elements. It turns out that in a generation of these heavier elements, I've talked about oxygen, I've talked about iron, but it's very difficult to get significant elements beyond iron out of supernovae. And it's been a big puzzle where gold comes from. I've got some gold. Many of you will be wearing a bit of gold. That's where they come from, neutron star mergers. That's the only way we can explain gold. And when they do this, they generate a significant mass of gold, about a moon's mass of gold. Now, before you sort of are thinking about a gold moon, it's probably spread in a load of bits, and it'll be a very difficult thing to get hold of. But anyway, I'm just trying to say many of the things I'm talking about are actually connected with you, not you in your current form, but the atoms out of which you are made and the atoms out of which your jewelry is made. Now go on to the final one. This is the ultimate one. This is the gravitational wave mergers of black holes. Two black holes can spiral together, and as they spiral together, they go faster and faster, and then leave behind a black hole. And the LIGO-Virgo consortium have got instruments now which are the ultimate rulers, which rulers in the sense of, measuring inches, shall we say. These things are, this is LIGO, which consists of this cross of laser beams are shining up there, and they are comparing these laser beams all the time. If you stretch that and don't stretch that one, then they'll get out of sync. And you can detect that down here. And you can detect changes in length equivalent to an atom, the size of an atom, versus the distance between the Earth and the Sun. That's the precision that they're making, okay, with these gravitational wave detectors, 10 to the minus 21, okay? And they switched Advanced LIGO on in September of 2015, and within 3 days, they had measured a merger. This is what it looks like. There's the oscillation. This is just a plot of, a theoretical plot of the strain. That's the relative motion of it. You can see the oscillation gets faster and faster as these two spiral closer to each other. They merge and then ring down. And so we've got it like this. Just to show you the data, here's the data like that. You can see this is frequency, that's time. You're seeing it for only 0.2 of a second, but it starts off with a frequency of somewhere like 40 hertz, and at the end it's gone up to almost 300 hertz. And this is this detector, which was in Hanford in Washington State, and this is the detector they had in Livingston, Louisiana. So they've got two of these interferometers in the US, and they were both working at the same time. They both saw the same signal. And in fact, you can take the signal from that one and plop it on top of the signal from that one, and you see that they match. So they're looking at the same event. They were extremely lucky, because this was the merger of two 30 solar mass black holes. Two black holes of 30 solar masses merging together, and they presumably formed one of a mass of about 60 solar masses. I say about because 3 solar masses was lost. It went into radiation, not into electromagnetic radiation, it went into gravitational radiation. And this is where it sits in this plot. Here's the ultimate power. Here's gravitational waves. That merger is up here. I've put it at low mass because it's 30 solar mass objects. I've given it green because it's not electromagnetic. Just for 0.2 of a second, the amount of power out of this merging system in terms of rippling space-time, the power involved exceeded by more than a factor of 10 the total power from all the stars in all the galaxies in the universe. So that, it got within 8% of the ultimate power, c to the 5th over g. I've now put everything else I've talked about on this plot. There are quasars, apparently can look brighter with jets, supernovae, gamma ray bursts. Supernovae, actually, most of the power of a supernova comes out in neutrinos, and the 1987A supernova collapse did create neutrinos, of which 30 were detected on Earth. Neutrinos, if you know anything about them, you know that they're ghostly particles which can go right through the Earth many times. So that's a power there. But this is where power lies in the universe. And I'm going to finish with a demonstration. But this is just, again, a representation of two black holes merging. If you were close enough to look at them against the Milky Way, it would look a bit like this. You wouldn't want to be this close, but okay, and here it goes. You get closer and closer, and space-time stops wriggling, and there we are. Okay, and there's just a nice picture of the Milky Way. There's the Large Magellanic Cloud, and there's the Small Magellanic Cloud. Now I'm going to show you just a chirp. What happens, the oscillations got faster and faster and then stopped. That's called a chirp, and that device I'm about to show you actually produces a chirp. And this is your take-home experiment, okay? Okay. Now, don't be worried about, it's actually a toy. Don't be worried about playing with toys. These are 3 Nobel Prize winners in physics, Richard Feynman, Wolfgang Pauli, Niels Bohr, 2 great physicists of the last century. They're looking at a toy. It's a top, a tippy top, one that you spin and it flips over, if you know what I mean, and they're trying to work out what's going on. This guy, Richard Feynman, was actually watching somebody spinning a plate in the Cornell cafeteria and realized that the motion of the plate was peculiar, and he worked out what it was doing. And in his autobiography, he points out that that broke through in his thoughts and ideas that led to his Nobel Prize. So what I want to do now is to show you a simple toy, and it's this thing here. It just consists of a heavy disc and just a plate to put it on. And I'm going to spin it now, and hopefully the camera will. Okay, it's now spinning. And you can do this at home with a dinner plate, okay? Do it on the floor. And the way in which it gets faster and faster, the rate of change of it is the same rate of change form as the merger of two black holes or two white dwarfs together. So it's going faster and faster and faster. And it takes a long time. But when you do, when you do the plate on the floor, don't worry, it will happen quickly. And you'll do it again because you realise you had the plate the wrong way round. And this will end, I hope, with a chirp, and that will be the end of the lecture. Yeah. Conservation of angular momentum, this is, yeah. It's, and I hope you can see the sort of holographic things on top. It's the actual thing's spinning faster than it appears to from there. Here it goes. Soon. Yes, very soon.
So, Andy, thank you very, very much. That was absolutely wonderful lecture. You know, you've taken us through huge distances and times, powers of 10 beyond most of our imaginings. I'm a geophysicist. Powers of 10 in the Earth don't go up that high. And yet at the end, you end with, in fact, demonstrating two black holes on what I thought was an orange from where I was sitting, but I see it's the head of the microphone. I mean, that was, you've talked about ultimate power. I think this is the ultimate lecture on astronomy. Thank you so much. Now, I mentioned that Andy's been the person overseeing this lecture series, this annual series, for some 32 years now. As you'll know, in recent years, they've been filmed and they're available online. So actually, sometime this next week, you'll be able to watch that again, see all these images again, and trying to figure out which one was 10 to the 26 and 10 to the 52. But each year, there's also a book is published with a chapter from each of the speakers. That's published by Cambridg University Press. Obviously, it takes a little longer than a week to get a book out, but hot off the press tonight, I have kind of a record book because it's the first book in this series that has the images in colour. So it was the Plagues book, just published. I think we have one copy here tonight. Hopefully far more, it'll be readily available from now on. It's got a chapter on Ebola. It's got a chapter on our Vice-Chancellor by Vice-Chancellor Leszek Borisevich on medicine and plagues. He's not a plague. He's an expert in medicine. So watch out for this one. Now, next week, we come down from the stars. We come back to Earth and actually worrying aspects of modern life with a lecture from Professor Matthew Goodwin from the University of Kent on extreme politics. But I think let's just end again by thanking Andy, both for tonight's lecture and for 32 years worth of lecture series. Andy.